Okay, so today we are going to solve this problem where we are finding the mass of a thin funnel in the shape of a cone. Z equals x squared plus y squared, all under square root, with the z being greater than or equal to 1 and less than or equal to 4. And we have a density function, 10 minus z. So the first thing I'm going to do is draw our funnel. Just so we have an idea of what we're looking at. And the second thing I'm going to do is to write out our equation for the mass, where the mass is equal to the surface integral of our density function over our surface. We need to parameterize our surface here. I'm going to first use the graph parameterization, where x is going to be equal to x, y will be equal to y, and z will be equal to a function of x and y, which will be equal to the square root of x squared plus y squared. Now we need to, with our parameterization, find what, we know that our ds is going to be equal to the magnitude of the cross product of our x and our y, which is the partial derivatives of our z, or g of xy, dA. And this cross product is going to be equal, or the magnitude of this cross product is going to be equal to the magnitude of minus x times x squared plus y squared to the minus 1/2 I plus y x squared plus y squared to the minus 1/2 j plus k dA, and this is equal to the square root of minus x over x squared plus y squared to the 1/2 plus quantity squared plus y over x squared plus y squared to the 1/2 quantity squared plus 1 squared. So this is what our ds will turn into, and then we will parameterize our density function, where we substitute our z in here. So now we have this double integral over a region of 10 minus the square root of x squared plus y squared times the square root of x squared over x squared plus y squared plus y squared over x squared plus y squared plus 1 dA. Now, looking at this integral, this double integral, it seems very clear that I would want to change this to be in polar coordinates. So I'm going to do that. We have, to convert to polar coordinates, we would have our x be equal to r cosine of theta, y is equal to r sine of theta, and then our r squared will be equal to x squared plus y squared. And as you can hopefully see, we end up with an integral like such, where we have 10 minus the square root of r squared times the square root of r squared over r squared plus 1 times our Jacobian, which is r, and then with our two differentials, which are dr and d theta. We need bounds for our integral, but we have this here, which if z is equal to the square root of x squared plus y squared, we can say that z squared is equal to x squared plus y squared, which is equal to r squared. Meaning that, and because both z and r in our case are positive based off of our bounds for z, we can say that z is equal to r and use the bounds for z as our bounds for r. So we have 1 is less than or equal to r is less than or equal to 4. And then, since it's the full circumference of the cone, 2. Is it 2? Yeah, sort of 4. But, okay. And since we're using the full circumference of the circle, or of the cone, our theta will be from 0 to 2 pi. Meaning that we have our final integral, which will look like 0 to 2 pi, integral 1 to 4 of 10 minus r times root 2 r dr d theta. And at this point, we can solve the integral. Which comes out to be this expression of root 2 times 2 pi times a minus 64 over 3, excuse me, minus 5 minus 1/3. Which we can plug into a calculator and get a more numerical answer than this expression. Anyway, this is the solution to the mass of our problem right here. And here are all of the steps we took in getting there. You might be wondering where this root 2 came from. It's right here. R squared over r is 1 plus 1 is 2 root 2. So that just about covers how we found this mass.